Hey everyone, Mr. Marone here. Welcome back in. We are in our last video for topic 3. We're looking at symmetry. So hopefully symmetry is something that you guys have seen in the past. It's when you can fold something in half and all of the points line up perfectly. You've used symmetry a lot growing up. My best example is when you were little and it came around Christmas time and you guys were creating snowflakes. So you'd fold a piece of paper in half, and then in half again, and then you'd make all sorts of little cuts. And all of those cuts would create these patterns. All of that had to do with symmetry because you were folding in half. That first one, the idea of folding in half, is the first type of symmetry we're going to look at. That's the one that's most common. It's called reflectional symmetry. They've got all the details here for it, but basically what they're asking is there a line you could fold the figure across that it would create all of the same points on the left and the right hand side. So they've given us 2 examples with this kind of wonky figure, and I'll let you read all of that information on your own. That's something that I think you're more than capable of doing. But I want to look at 3 examples here when it comes to reflectional symmetry. So it says, wood transformation maps the figure onto itself. When they're asking that with a focus on symmetry, they want to know, can you draw in a line that causes the figure to be symmetric? If I look closely at this green figure here, if I were to draw a dotted line right down the middle vertically, the left and the right hand side would be exactly the same. If I went horizontally through the middle, the same thing is true. Obviously my drawings are not very good, but you guys get the idea. With your physical papers of these notes, you could fold them in half and see it as well. So there are 2 lines that allow us to do that in that figure. 2 lines of symmetry, of reflectional symmetry. In our second example, in the smiley face, we can draw a line right down the middle from top to bottom, and that works perfect. But if I go across, the mouth won't line up, the eyes won't line up, so that one doesn't work for us. So in this case, we only have 1 line vertically that works for it. And you're going to do this process with any sort of figure given. Can you fold it in half? And that's what they're asking when they say reflectional symmetry. So if we look at this hexagon, how many lines of symmetry does it have? I can draw right down the middle through the middle of each side of my hexagon, and it's going to work. I can also draw a line through each set of vertices, those corner points. As you guys well know, I can't draw straight lines, but you get the picture. So in this case, for a regular hexagon, it's got 6 lines of symmetry. What's kind of cool is when you have a regular figure, when all of the sides are the same and all of the angles are the same inside of a figure, the number of sides is going to match the number of lines of symmetry. So just kind of keep that in mind. Okay. Now, the second type of symmetry that's less familiar is called rotational symmetry. In other words, how can I rotate a figure and have it copy or be the same thing as itself? So if we look at this equilateral triangle where all 3 sides and all 3 angles are the same, if I were to turn the figure 120 degrees, that first turn, I get the same thing back. And then if I turn it 240 degrees, I get the same thing back. And then I turn it 360 degrees and I get the same thing back. So whenever you're looking at rotational symmetry, they want to know how many times can you turn the figure before you get back to the beginning and still have the same thing. For an equilateral triangle, we can do that 3 times. We could turn it at 120, 240, and 360, and we still get the same figure. Where with a parallelogram, we can rotate it 180 degrees and then it's going to sit back on itself. If I turned it 90 degrees, the figure would look something like this. So that doesn't work. But if I go a full 180, it sits right back on itself. And they've done a great job in both pictures of labeling this. And then we can turn it back to 360. So it's basically, in 360 degrees, how many times does it repeat itself? And that's the number of lines of symmetry, basically. It's its equivalent for this. When you've only got the ability to turn it 180 degrees and have it repeat, and then 360 like a parallelogram, this has a thing called point symmetry. That's when there's only a rotation of 180 degrees, giving us our symmetry. So taking a look at these pictures here, they want to know what are the rotational symmetries for the figure. And they want to know, does it have point symmetry? So in this kind of pointy compass looking thing, I can turn it 90 degrees this way, and it's going to sit back on itself. And then I can turn it 180, 270, and 360. So those rotational symmetries are 90, 180, 270, and 360. And since it has more than just 180 degree rotational symmetry, it does not have point symmetry. And then in our last example here, they want to know what type of symmetry does this figure have. So if we look closely, we can rotate the figure and have it stay the same. But at the same time, the veins in the leaf aren't going to be exactly the same. So this doesn't have any symmetry because of the pattern. If it was just a solid purple star, we could do symmetry. But since the idea of symmetry means that we can turn it or flip it or cut it and it would have the exact same thing, doesn't work in this example. So those are the three types of symmetry. You've got reflectional, rotational, and then that idea of point symmetry, if you can only turn it 180 degrees. Great examples of that are the parallelogram. A rectangle is another really good example of a figure with 180 degree rotational symmetry that also gives us point symmetry. If you guys have any questions, bring them into class tomorrow, and I will see you then. Have a great day. Bye.